So this Prusa MK3 is bone stock. Or is it? This is the standard extruder and hot end assembly from the Prusa Mark III. The hot end itself is an E03D V6, arguably one of the most influential hot ends of all times. Just like the Prusa MK3 is by itself. One of the key selling points of a hot end is how much material it can melt in a given amount of time. This is called volumetric flow and it is measured in cubic millimeters per second. With a well-tuned filament profile, this setup is good for, let's say, 15 cubic millimeters a second. And this flow rate has been working flawlessly for, let's say, a decade. But then, in the last couple of years, a lot of stuff has changed in 3D printing. And the demand for even faster machines has grown ever since. Nowadays, the motion system isn't the limiting factor, it is flow and cooling. And that's why a lot of companies are pushing in the market to develop hot ends that can easily just melt more material. And that's also what I've been doing here on the Minuteman machine. So you may or may not know this hot end. This is capable of around 400 cubic millimeters of flow and it is a complete one-off prototype. So today in this video we're gonna use this technology and put it on this poor Prusa MK3 here. So I've already done a lot of testing with this kind of Bowden setup here. What you will see first is the extrusion test with all the temperature I've got to see where the absolute limits of this setup actually are. And then we're gonna rebuild all of this to a direct drive setup. I have all the components sitting here. And then at the end we're gonna compare the two and see where our actual limits with both of these setups are. And I think then we're gonna print some pretty fast benchies. I don't know. Let's see how this goes. So my name is Jan. I build stuff so you don't have to. And now you will be seeing an intro with this exact Prusa MK3, which I own since 2018. Enjoy.
Da 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 da.
So this test was designed to have continuous flow starting from 80 cubic millimeters all the way to 175, but I chickened out at around 150. You will have seen that on the screen there. Well, because I didn't want to bring out the fire extinguisher. So as I said in the last video, at some point you will be having a download link for this kind of hot end where you can basically get all the materials you need from your online or local manufacturer. So one of these online manufacturers is PCBWay, and this happens also to be our today's video sponsor. So all of the parts you've seen today or on the Minuteman machine are mostly produced by them. And once I publish the files, it is as easy as just going on their website, uploading these files as STEP or STL or whatever, selecting the right material, which I think will be aluminum, selecting the desired quantity, and you basically get an instant quote on all the parts you want to have. PCBWay does a lot in terms of 3D printing. So for example, this is a polyjetted nylon part. This is SLM printed from solid aluminum. This is SLM printed in stainless steel. But they also do a lot of different stuff. So basically you name the process. This is a part that has been on the Minuteman machine. It is manufactured in sheet metal process. They also do PCB manufacturing, of course, and CNC milling in 5-axis, basically everything you need. So there will be a link down in the video description where you get a small discount on your first order there. I can highly recommend their service. Thank you again, PCBWay, for sponsoring that content. Just as a quick note right now, it won't look anything like this. This is just because I had to use what I had on hand, and I designed something just to hold it there and basically get the nozzle in somewhat of the same region as the original E3D one was. So this is our part. As I said, 80 to 150 cubic millimeters. It's looking quite alright, huh? There are some very small artifacts, but I haven't dehumidified this filament before. So this hot end isn't only capable of extruding vast amount of filament. Have a look at this. Since we're using two filaments at the same time, you'll get in effect something like this. So in this example, we're using this hot end technology for creating unique colors. In this case, both of them are a bit transparent, so we don't get that sharp transition as we would get from a matte filament. We'll do that later on. But what we can also do, I mean, that's not part of today's video, but we can mix filaments. So basically you have a hard shell like PLA, but a soft TPU core or whatever you come up with in terms of combining. I mean, mixing isn't the right word because we do have laminar flow all the way, but we can combine filaments and use their certain properties. So in an upcoming video, I want to try to 3D print a speaker, or I mean more precisely the voice coil, by using a non-conductive outer layer but a conductive shell. And I want to see if I can 3D print a coil in one go in vase mode, basically. I've already printed stuff as a preparation for this video. There is some kind of benchies, there is pressure advance tests, basically you name it when it comes down to getting something like this dialed in. Yeah, but this is kind of an approach where this is pretty much lightweight. All of this is around 200 grams, so comparable to very light hot end setups, and it doesn't take up too much space. Since this is a quite small machine, I found out the hard way that it is not even that easy to run this kind of flow on a machine like this. You end up in all sorts of problems because, for example, this is what I printed a few days ago, and this is a very fast first and second layer. And while this heat bed has been sitting at 55 degrees for standard PLA printing, after this amount of material, the heat bed temperature has raised to 80 degrees with, basically the heat controller turned off all the way, because there is so much flow so much energy just flowing onto here that it has raised temperature by over 35 degrees on that massive metal plate there. So yeah, you run into new kind of problems, and that's why I want to check out the direct drive version of all of this. So we're basically gonna stick this extruder up here. We'll lose some kind of travel in the X direction, but I think for the tests we're running here, this is completely fine. It will still be kind of a lot and a lot more than on a Minuteman machine. So let's have a look at how we do that. So what I've always loved about these Prusa printers is how accessible and modifiable they are. Because everything here is designed to be repairable. All these parts are online, so you can just download and reprint them in case you, I don't know, crash the machine or whatsoever. And I think this has gotten way worse over the years when you consider the new style machines. So with this hot end, I basically try to do the same thing. It should be repairable, it should be modifiable, and at least somewhat easy to integrate into existing systems. So that's why, even though, again, this is nothing you would be downloadable, I mean the whole contraption here, it will look completely different, trust me. But we need to do some more testing before we can go into deep CAD. But I needed to do some real-world printing and not just extruding on a test stand. But if you have a look at here, this is the original Prusa cold end fan, which I'm reusing. These are original Prusa linear bearings. I'm using the original Pinda probe. So basically the only thing I added here is different heaters and thermistors, because we obviously just need a bit more power. But this is it, and I want to try to keep it this way. So now, let's get on with all of this, integrating this up here. I had a few options where to put this. I could either have gone like this, but in the case of the MK3, I would have hit that and lost a lot of Z travel. So I decided to go with this kind of orientation. I have my 0 point probed here. So basically I have to restrict that movement to the left-hand side. And we're losing our, I think it's somewhere around 45 millimeters. It's still kind of a big surface area. It's like 200 by 200 we can use and 180 or something in Z height. There is a bit of travel lost, but we'll get rid of that in the future iterations. I'm pretty sure about that. So let me finish my conversion here. I really like the appearance of that model. And in terms of parts you can use from your original i3 MK3, this spool holder typically just holds 2 of them. But yeah, you can just use the middle lane of that spool. I don't know, maybe it's just the way it has to be. Yeah, I just put in some material here. That does work. No more leaks than it was doing before. So yeah, basically I want to do what I have done before with the Bowden setup. So we're gonna run a few pressure advance tests and yeah, see how this applies to real-world applications like printing a Benchy or something, and then we'll repeat the flow tests. And yeah, see which one of these systems is superior or where are the pros and cons to each one. Let's do that. Alright, so first results are in, and it is not a surprise that a direct driven setup does need lower pressure advance values than a Bowden setup does, but the amount it differs really surprised me. So let's have a look. I did 2 tests for the direct drive and the Bowden drive at 200 degrees and then at 225, just to get a few more data points. And you can see basically these are both of the results. I mean, these are not the same range. This is more with a coarser resolution than this one is. But in both cases, I did a test beforehand to see in kind of which range we're dealing with, and then here I did something from 0 to 0.12, and in this case I tested 0.4 to 0.7, I guess. But you can see that these really do look fine at certain points. This is essentially what this test is trying to tell us. And there seems to be an order of magnitude between these two. And what this means, this is in seconds. So basically what our extruder is seeing as a kind of like look ahead function on the G-code. So basically in this case with the direct drive setup, there is 0.05 seconds it does the move before it actually is needed down there at the nozzle. And in this case, this is more than half a second. This does work for slow prints, which we had in the past. But even with this kind of material flow, this is, by the way, a 1mm nozzle that is doing all these tests. And everything here is extruded at 50 cubic millimeters a second. That is not anywhere to be seen on like these hot ends from the past. Even with this kind of flow setups, we encounter these values are quite high. But then again, we'll come here in a second. If they are dialed in properly, you can expect pretty great results. And the bigger, and this is also being extruded with a Bowden setup, the bigger the parts get, the less the system actually does care about it. But of course, in terms of like printing a 3D Benchy or something, a lower value is always preferable. I mean, the lower value is always preferable, but there are certain subcategories where you can get away with a high one and where a low one is really needed. So as I said, I took two data points, one at 200, then at 225, and you can see that these pretty much fall in line with each other. There is basically an order of magnitude between those. This is 13, this is 5. And I have no idea how much of that shiny filament is gonna be picked up here. As you can see, the viscosity is a whole nother level, so it shows a lot of defects. This 200 degrees is the rated temperature for my kind of flow. I also tested that beforehand. So this shows a lot more of defects because the material is way more viscous. But that is also something we do have in our day-to-day printing. So this Benchy had like 130 something cubic millimeters of flow here, and when we came to the pillars, it is less. But you have to dial in temperature for this part, so the hot end will make this extrusion move, and then it comes out way too viscous up here. This is basically what I'm testing here to get a few more data points. So the next one we'll do is basically repeat the retraction test I did with the Bowden setup. And you can see that we pretty much lost the stringing up here. This is 10 millimeter of retract, but before you lose your mind over these values, you have to basically divide them by 4 because it is divided onto all of these parts. So this is basically 2.5 millimeters of retract value, which I think is pretty good for a decent printing temperature and a 1 millimeter nozzle. So let's see how much of a retract we have to do with this kind of direct drive setup. So the first one is done at 215 degrees, and basically this is 0 to 2.5 millimeters of retract. You can see that within a reasonable range I couldn't get rid of the stringing. Then I opted to give it a more realistic temperature. This is at 200 degrees, the same retraction values. And when I couldn't even get these to be stringing free, I also tried to give it some wiping distance to clean the nozzle before retracting to the other side. As you can see, all of these still do have some kind of stringing left. I mean, of course, this is one of the worst things we can have for a hot end. We just have so much molten material up there and gravitation is bringing that down. Everything is kind of designed to feature max flow. And then we have a very big orifice strapped to it with 1 millimeter right now. So of course this is like a pretty hard test, and I think this is not too bad here. But of course I would like to get this stringing free for the future. I will set this aside for a second and repeat this once I have a different nozzle installed there, maybe something in the 0.5 range or something, and we'll see if this is purely nozzle related. But I think what we need now is some kind of printing of a real world object. Let me see what I can find. Alright, I want to see the reliability of the system and do a proper run with some height in it. So this vase is 135 in XY and 116 in Z. And we're gonna continuously extrude with 100 cubic millimeters a second. And this would result in 120 grams in just over 30 minutes, if the estimation here in Orca Slicer is correct. I will be printing at 230 degrees. This came out right around perfect at 105 cubic millimeters of flow. So let us put that on the machine and see if we can finish a print. What have I got? We're extruding with a 2 millimeter outer wall line width. So 1 millimeter nozzle extruding 2 millimeters wide to even get close in this flow area. So I'm going conservative here because I don't want Clipper to shut down the printer again because bad temperatures are behaving weird. You can again see the bad warping in the middle, just because of all the heat that is being dumped into there. So this guy finished in 28 minutes. This is a clear sign that the Clipper or Orca Slicer estimator is not fully configured for this part. It was estimated 32, and I was fooling around a lot with the 3 solid layers down here. These were not at the calculated weight, way down, sometimes at 10%. And then it is calculated at 120 grams of material, so we don't seem to have any kind of under extrusion. Let us have a look at that in the light outside. So I guess from certain angles this just looks like a mixture of the 2 colors, but then again you can see these shimmering colors in between. I have no idea if the camera can pick that up. So just as a quick note, if you want to get more involved in this project, I highly recommend to join my Discord server. There is a link somewhere down in the video description. And there also is a link to my Patreon account. And here goes out a special thanks to all of these people who make projects like this possible. Thank you. Alright, so this is something you would see at a trade show, because this is pretty much the easiest thing you can do in terms of 3D printing something. It is the vase or vase mode, whatever you pronounce it. Because basically the printer doesn't have to do any retracts or weird moves or something, and you basically have one profile that has to be dialed in, and that is running continuously. And usually you don't end up with problems with cooling, etc. I do run into cooling issues again. It seems like the curse of my last year, having cooling issues, but I would need to slow down printing to have perfect layer cooling. A 3D Benchy, on the other hand, does feature all the things you face in day-to-day 3D printing, from overhangs to having real high flow and low flowing areas throughout your print, from heavy bridging all the way to hitting tolerances. So let's have a look at my screen. Alright, so this is the Benchy we're trying to print. This is scaled up to 250%. And we're still using a 1mm nozzle, we're still using 2 parameters and an extrusion width of 1 to 1.1 millimeters essentially. The speeds are set to 400 millimeters a second for all the different lines. Then we have accelerations from 5K to 10K for travel moves. Looking at the filament tab, we're still using 4 spools of Fiberlogy high flow PLA, 2 in burgundy, 2 in turquoise. We don't run any retracts here. In terms of cooling, I set the minimum layer time to 3 seconds. Put in our previously experimented pressure advance values somewhere in the middle between those 2 temperatures, so middle of the viscosity you might say. And then last but not least 150 cubic millimeters of volumetric flow. And this comes down to 1 hour of printing time, estimated at least, and we're using 152 grams. This results in a pretty even speed throughout the print of, let's say, somewhere in the range of 350 to 400 millimeters a second, but then just here at the pillar part and also at the chimney, it slows down quite a lot. And as you can see here, in a perfect world where we don't have accelerations and stuff, we're pretty much consistently extruding at, let's say, 130 cubic millimeters a second throughout all the print and all the different lines. But now, let's see how much slicing differs from actual printing. As in the last video, I've shown this tool by Salim. This is the SB53 temperature controller, and it's pretty much a post-processor for your G-code that is analyzing how much actual flow is being delivered, basically taking into account the accelerations that the printer is going through. And you can see here on the left hand side there is the flow in the graph, and here on the right hand side there is the temperature curve. And if I hide everything else, this is the average flow per second, and you can see that it is right here somewhere in the 64 whatever range, basically topping out at 120 or something, but also a lot of moves are somewhere here in the 20 cubic millimeters range. And what has become a real important factor is that we want to have consistent viscosity of the melt throughout our print. And the bigger the requested flow is becoming, the more of a problem it is to deliver everything from that huge range of requested flow, essentially, with a single set temperature. So in terms of a regular 3D printer, that may differ from like 5 cubic millimeters to 12 or something, so there isn't that big of a range. But if we're dealing with from 20 to 120, that is a different animal. This tool, or other approaches in like Danger Clipper or whatever actually allow us to dynamically adjust hot end temperatures throughout the print, and this is what we're doing here. So as you can see here, we got some set values for different flow rates and different temperatures we want to achieve there. So now the tool has analyzed the G-code and has given us a perfect temperature for the average flow in a given time frame. So if we have a closer look at that here, we can see that this is calculating an average of the requested flow and then applying the appropriate temperature to it. And that is doing that throughout the whole print. You can see this area here, where you can zoom in, this is like the part with the pillars growing up. We have a very limited flow because it is limited through our layer times. And we're counting that by going down with the temperatures all the way to, let's say, 190 degrees or something. And yeah, by hitting that generate button, you can actually just have your G-code overwritten with the appropriate temperatures with a look ahead function. So we have a temperature rise and fall value over here, which is set to 1 degree per second because we have a very big hot end. That right now isn't the most dynamic, but I think for this printing scenario, this is a good fit here. And the look ahead function does give, like, if we want to have a rise in temperature by 20 degrees to increase our flow, then it's basically giving the command 20 seconds early when we need that temperature. And now we can upload this to Clipper and have it a go. So this is the back side of the finished print. Let me take it off the build plate, remove the stringing. This is just distracting us. There is a bit of stringing, but I don't think it's too severe for that kind of delicate print. And then we'll have a look from the other side. So of course, this Benchy isn't looking perfect, but as always, you're not seeing like a polished version of whatever. You're right in the process of me just finding stuff out. And this is like the, I don't know, 5th or 6th print we've done with this kind of setup. There is literally nothing done in terms of input shaping or setting some kind of, I just used the standard Voron profile. And you can see there is a night and day difference between the left and the right hand side. This was here like this on the build plate. So clearly my cooling solution here is doing asymmetrical work. So let's just assume it would look like this on all the sides. Let's talk about cooling for a brief moment. So right now you see my compressed air setup, and you've been asking me in the comments if we can go a different route. I'm 100% on that. This is just the most potent setup I have here right now for a hot end that is not heat shielded. If I would run some kind of a big sheet air something, I would blow this guy cold because it doesn't have any like silicone sock or something. I guess the next version I'm gonna be prototyping will be CPAP based. And yeah, this guy took pretty much 54 minutes. I like the feeling when you take this off the build plate and set it on the scale. It's just a bit weird. This is 4 grams more than it was estimated, maybe 3 grams. So we don't face any problems with under extrusion. This guy just works. This tiny little motor, again running at 1 amp, is just pushing all that material through. And this is possible because we're using the very first and most important rule of extrusion in an FDM-based system. We're not running things at above 80%. The amount of work an extruder has to do to get out the last few cubic inches of material deposition is just off the charts. So by staying in the range and adjusting our temperature dynamically, we do have pretty constant viscosity. We don't encounter big die swell or something. It just works if we keep that in mind. And to set this into perspective, let's hop back on my screen and I will show you some comparison to existing printers. Alright, so let's talk a bit about flow rates and actual decrease in printing time. So I got, you've seen this slicer already, but I've set up the same thing in Bamboo Slicer. And the profile we're using here is basically standard stuff from BambuLab. We're using the X1 carbon with the biggest nozzle you can have on shelf, the 0.8. And we're using a generic PLA profile where we say we can run 50 cubic millimeters per second continuously. That is the catch here. So maybe there are hot ends out there that claim to do 70 or something. And maybe in cases of printing a Benchy or something, they will do that, but it's just peak flow. There are certain regions where you might peak 70 cubic millimeters, but you would never do that on average. As seen here in the latest print, if you just divide the filament being used through the 54 minutes of printing time, that comes down to around 40 cubic millimeters per second on average. Still, there were times where we've used like 125 or something, but on average that is a totally different thing. And I can guarantee you that almost the entirety of hot ends that claim to do 70, 80 or 90 will not do that continuously. Maybe if you run them at 300 degrees or something, but this is not what we do want here. Alright, so I fooled around a bit. Again, everything in the favor of the BambuLab. Pretty high flow hot end on there. And I've basically matched the filament used throughout the print by playing around with perimeter walls and infill. And you can basically see this estimation can be considered pretty accurate. And in the case of on the Prusa machine, as I said, this run 54 minutes. So it is not half the time, but pretty close to that. And this goes to show with a very delicate part like a Benchy is, the difference is notable, but not really too far off. We're not completely comparing apples to apples. This is the 0.8 nozzle. This is 0.4 layer height, and in the case of my machine it's 1 millimeter nozzle and 0.5 layer height. But essentially we're trying to extrude the same amount of material, so it will be a pretty good comparison. If I would like up my input shaping settings and run the same acceleration values as on the BambuLab, which this machine would surely do, I guess we would pretty much be at half the printing time for the same model. The point I'm trying to make here is, I've sliced this cylinder with a given amount of infill in there. A pretty big part. This has a circumference of 165 millimeters and is 100 millimeters tall. And this would consume 450 grams of material and would run pretty much 3.5 hours on a BambuLab with everything maxed out in terms of continuous flow. If you have a look at the same slice on the Prusa machine right now, this is again at around 450 grams. This estimator is way off. If I put that same code into the SP53 tool, this is running the clipper estimator in the background, and this seems to be pretty spot on. Let's not go into a favor and say this has taken an hour. But you can still see whenever we have a print where we do actually reach our target speeds and therefore also the requested flow, then we can actually cut printing times by a lot. This is by a factor of 3. Of course, we don't want to compare apples to whatever. This is different layer terms, but I just want to give you an example of which cases this hot end might be your best bet. For small and intricate things, this might work too, but I just don't see the point. You can like type in 200 cubic millimeters of flow on a normal sized Benchy. No printer in the world, even the Minuteman machine, won't reach that extrusion values. But if you are building like really large structures on a lot bigger machine than, let's say, an MK3 or a BambuLab machine, well, yeah, then it is a great time saver to actually use a system like this and deploy all that flow you got at your disposal. The limit of cooling stuff down again is unchanged. It is still our biggest barrier we're facing right now. So the bigger the part is, naturally the layer times will grow, and that will help to not have use liquid nitrogen to cool down your extruded filament. It will just cool in time by itself by a normal stream of air around it. This Prusa machine is running great and we'll do a lot of different testing on it, but in the future we will need a bigger machine for sure to really give it the beans and even get the chance to extrude at like 300 cubic millimeters a second or something continuously. I don't think we can do that on this machine. No matter how big and wasteful I design the prints there, layer time is just causing this to not work or look bad because there is just not enough time to cool it down in time. The hot end will deliver two things that are out of its class. And first off, this is of course the flow rate you can achieve. The second thing is the different co-extrusion modes, so where we can combine colors and different raw materials to create essentially new filaments in line. We will focus on the second part in the next video because I have so many options on the table in terms of how many filaments and in what kind of combination we'll put them. I think for coming to an end of this video, we're gonna repeat the maximum flow calibration. This time I'll try to not chicken out and just run it all the way to the end. Just as a disclaimer, this is just like we discovered in the last episode. This is our standard geometry with just straight lines going down SLM printed. Next time we will go into way more details regarding how can we manipulate the filament inside of these channels, and the approach with the flat geometry inside suggested that we can up our game by at least 30% per channel. Take all of these numbers we get now with a grain of salt. If we can reach, let's say 170, 180 continuous flow, I think we can make it all the way to 200, 250, somewhere in that range if we apply everything we've learned so far. So let's hop on the printer and yeah, let's lay down some material. have a look at that. So even with our standard geometry, we have successfully managed to extrude, I looked it up in the footage, 193 cubic millimeters, and it was still going. And as you can see in the overlay, we were requesting 270 degrees, but the heater was hard stuck at 255 and therefore then triggered an error because, yeah, for unexpected temperature behavior. But yeah, this has really solid layer adhesion and everything. So the way we can control viscosity over the flow and therefore adjusting the temperature is working really, really good. So there you have it. This is 100 grams of filament in 8 minutes or something. So by just guessing the numbers, I think we even had like 200 or even a bit more would have been possible in a continuous flow scenario. So with all the optimizations we can do in terms of channel geometry, I think it's fair to say that we will surpass 250 or something. I'm pretty hyped about that. So let me see what I can do in terms of future iterations. So in our side quest of developing a really high flow co-extrusion SLM printed hot end, we've already achieved a lot of cool stuff. So in the last video, which was the first on this dedicated topic, we tested a lot of different geometries and did some basic flow tests with it. These gave us an overview, which is like a drilled straight channel compares to an SLM printed channel and what kind of shenanigans we can do to improve our melting capacity right there. So this video was all about verifying these results in real-world printing applications. Because just extruding in free air doesn't give us any feedback on how it is actually working. So that's why there is this Prusa. And if you have a look at here, this is a comparison between the original extruder and what we added on top. As a side note, this original Prusa assembly is somewhere in the range of 530 grams, I guess. And this whole complete assembly is about 630 grams, so 100 grams on top. So the next video will not be about finalizing everything we're doing here, but I want to give you the first downloadable files. I will construct the whole thing, get it over here from PCBWay, and then test it on the machine. And if I'm somewhat in the right range, I will publish the file so you guys can put it on your machines too. I will be also posting everything regarding the Prusa MK3 because I think this is a printer that has a lot of potential, is bulletproof and can pretty much use with original hardware using this kind of style. And we'll do the integration either with the Bondtech extruder, which might become a product in the future, but also with off-the-shelf solutions that don't break the bank. So my predictions for what the final hot end will look like, well, yeah, basically not anything like this. My main goal is to use as much of standard parts as possible. So we, well, yeah, have these two big components, SLM 3D printed, and then I will try to get you a bill of material with like standard wrap style M6 nozzles, with standard heat breaks, with standard part cooling fans and fittings, all of that. And what will be inside the hot end will also be determined by the next iteration. As a quick look ahead, what we're also testing in the next episode. So you know this here, this is the straight channel, this is flat geometry, we're gonna have another control group here. Then we're going to test if it is beneficial if, like, get a better heat transfer at the very start of the entry. And I think you're gonna be interested in this one here. So basically we're testing if the ripples of a golf ball are beneficial. We're gonna test something that like pulses the filament. We have some spirals in here. We're gonna do a whole lot of testing in terms of the flat geometry, dwelling the filament, making this channel longer, having it in 3 dimensions. And also do a whole lot of stuff regarding getting better heat contact to the core of the filament. And then in terms of the hot end itself, my plans are to publish files for a 2 filament version as well as a 4 filament version. And then there are going to be different subcategories. So the 2x version will focus heavily on just creating a lot more flow. And the 4x version will of course also do that, but then I'm gonna focus on multicolor integration. I'll try to publish both of these so you guys can actually help me in further developing that, because in my limited time it is very hard to do proper optimization of filament profiles and all of this stuff. So I can hand out a mechanical solution to all of that. It will be labeled as a prototype thing. So this isn't a final version of something, but it will be the 0. whatever version that I'm going to publish. And I'll disclaim that at every given point. And once we got some more data, we will finalize that and make it a real product. So as always, it was a pleasure to have you guys on board for my shenanigans here. I hope you found that out of interest and are, I hope, hyped to maybe rebuild your MK3 or whatever machine you got on hand. Maybe make the conversion open source as well, give others the tutorial on how to do it, and grow the community even more. And with that being said, my name is Jan. I build stuff so you don't have to. See you guys in the next episode. Bye. So this Prusa MK3 hasn't been touched inappropriately.